Good evening and welcome everybody. It's Obi-Wan Pez for N Simplex Pachinko with a super late start tonight, but yeah, it's fine. Hope y'all are having a good evening. Still says we're on ads for like 25 seconds. I don't believe it for 1 second, but hey, whatever. Huh. Alright, whatever. Anyway, having a good time. Went to do a couple of things tonight and just kind of got lost, so it's all cool. Not in real life, just in my head. Quite strong. I think I might have left the red Assam tea steeping a little bit too long, but it's alright. Well, unfortunately, Zach, this is one that we've already talked about on stream a couple weeks ago. Alex Kontorovich opened up this Diamond Open Access journal, which was trying to go beyond open access. So oftentimes in open access, you also have to charge the person who is publishing their article, I think it is. Whereas with Diamond Open Access, both the people who are getting access to the journal and the people who are being published in the journal are going to be at no cost. The trick then, as he mentions in the article, is to try and get funding from somewhere. But the good news was that he and his team worked out that it costs somewhere around like $3,000 per journal per year. And especially once you start getting beyond the first journal, if you're publishing multiple journals in your team, then the cost starts diminishing, just because you've already got some of the overhead taken care of on the first journal. So we were reading through this bunch of weeks ago. I just kind of threw it up there because I have nothing on my whiteboard. And that's very boring. I cleared it thinking we were going to do some more stuff on Monday, I think, and then stream died, so I was like, well, that's not helpful. I also have to do my trivia. For anybody who hasn't been here, yeah. Yeah, and, to get it, professionally done. So the other big part of it that was what else do we need to do in order to ensure that this is at no cost, is that members from the community would need to go out and be the referees for this stuff. And I was mentioning that I know if I was in, say, Penn Center's position of being a department chair, that would be one of the ways in which people from my community college, for example, or my department if I'm working in a larger school, could contribute to a larger community. Is you get a few hours a week taken off of your commitment to the school in order to be a referee for a journal. I don't remember exactly what the numbers were, but on our end of the year reports, you had to have something like 80 hours of work for the school and something like 100 hours that was work for your department outside of teaching. So like going to an event, going to a 5K and assisting people in whatever capacity, it didn't really matter. But if you volunteered for it, you might get like 2 hours on a Saturday. So that would count for, 2 of your 80 hours. And for instance, if you volunteered for a journal, I would lobby for, somebody getting up to 2 hours a week to be able to be a referee for a journal or something like that. Take that off of the extra duties for the department, for example. I'd have to work it out with the particular school and make sure that the individual is actually doing it and whatever. But anyway, none of that may matter anyway. I'm just going to be weird. No, in another year and some odd, see this space for what I might be doing when I move back to the States. But I've got some ideas anyway. I have essentially, at this point, a few small minor prospects. I know you were saying like being able to write that book that you were thinking of would be like would be really cool if you could get that done before the end of the year. There are so many random little projects like that I've shoved into the back of my head at this point. And right now the priority is finding a new place to live. So once we have that new place to live, if there is enough space for an office, I will be getting my own office, so I don't have to put up with that. And then I can maybe start working on, or restart working on some other projects that I've got. We'll see how that goes. So how's it going? Haven't seen you forever, like, 2 hours. These are always fun little questions. If f is continuous everywhere, if f is continuous everywhere, what is the value for k? All right. Yeah, Zach, you'll really like the couple of places that I went by myself to look at apartments and condos and houses this week. It was borderline staggering. So many places, and I grant you, a lot of Britain is like this, but so many places have unchecked mold. It is just unbelievable. And I can't say much because Maryland isn't much better. But nonetheless. It does. How you doing, Killer King? And like, you'd think it would be mostly frozen in the winter or something like that, but nah. Just means it pools more. We actually went to Tromsø, Norway last week, and we saw snow for the first time in snow on the ground for the first time in like a year and a half. we had one snow day for the kids last year, and it was rather pitiful. The only reason that they had to stay home on a different day was that it rained and then froze, so everything was slippery. I didn't stress about that one too much. That was very understandable. Okay. So if f needs to be continuous everywhere, what is the value for k? So definition for continuity, just real quick, as a reminder, right, we have to have 3 rules that were followed here. So first of all, okay, we should probably describe the space we are working in here, ish. Fine. It's not that either. So for all of the points, or for all of the x values within the domain of f, let's define some function f that we're working for here, or working with here. And in this case, we could just think about the f that we have there. The point that's fine. Paint myself into corners every single time that I do this because it's like, no, you can't do that. The point yeah, it's fine. The point x comma f of x must exist. So you should be able to plug it in to the function and just get something. In order for it to be continuous, though, we need to also have some other ground rules. And the next big one that comes up is that the limit as x approaches see, I'm painting myself into a corner again. It's fine. Hey, Ben. How's it going? Okay, so for all x within the domain of f, and for all x equal See, I don't even know how to... That's too programmy. For all x equal c, which is now in the domain of f, sure, we'll go with that. The point c comma f of c must exist. The limit as x goes to c of f of x must exist. And third, the limit as x approaches c of f of x needs to be equal to the limit value, which is f of c, the original thing that we had at that particular point. So again, for continuity, this is how it works. So we have to show that the point exists, we have to show that the limit around this thing exists, and we need to show that those are the exact same thing. Ah, well. Now, there is a bit of a shortcut in this particular thing, and that is that stage 1, we could just show that, okay, if we plug in f at 2, right, we get k. Okay. It exists because it says it exists. Number 2 says that the limit around this stuff must exist. So we have to show that the limit as x approaches 2 is going to be equal to some L, which is a finite, well, it doesn't even have to be a finite limit value, but it needs to be a limit value. Instead of being, again, something like that, which is not going to work. If we have something pointing up here and something pointing down here, you know, those are not going to point in the same place, so that's a problem. Nope, never mind. I was like, yeah, we could just say it works because this is a continuous function. It is not a continuous function. We don't know that. And in fact, it should not be a continuous function. Otherwise, they picked a very boring example. So we should come over here and say, okay, what happens when we get x squared minus 6x plus 8 over x cubed minus 2x squared plus 2x minus 4? Take the limit as x approaches 2. So, first things first, try and plug in 2. So we get 2 squared minus 12 plus 8 is going to be 4 plus 8, which is 12, minus 12, which is 0. And then, on the bottom, we're going to get 2 cubed minus 2 times 2 squared. Well, that's 8 minus 8, so that's 0. Plus 2 times 2 minus 4. So all of this is going to be equal to 0 as well. Therefore, this is going to be equal to 0 over 0, which is indeterminate. So, indeterminate form, we can immediately use L'Hopital's rule to say, oh, well, we did this last time, right? The limit as x approaches 2 of x squared minus 6x plus 8 over x cubed minus 2x squared plus 2x minus 4 is going to be equal to the limit as x approaches 2 of the derivative of the top divided by the derivative of the bottom with respect to x. So if we go like this, and then we leave this book open somewhere else, not in my hand, copy, paste, drag that on over, and then, nope, copy, paste, Drag that on over. Close brackets. Everybody's happy. Except maybe Zach. I know you've probably got an objection. That's fine. Okay, so in this case, we got 2x minus 6 divided by 3x squared minus 4x plus 2. And then if we plug in 2 for both top and bottom, we end up getting a 4 minus 6 over, good, not indeterminate, woo. Right? Yes. I'm just distracting myself. It's fine. Negative 2 divided by. Here we get a 2 squared is 4 times 3 is 12, minus 4 times 2 is 8 plus 2, so 14 minus 8 is going to be 6, which is a negative 1/3. Okay, so the limit exists. Therefore, by condition 3, negative 1/3 equals L, which equals F at 2, which equals K. So, K is going to be equal to negative 1/3. Got to make sure you follow the logic of all that stuff. It is a little bit ridiculous, and this is like overly explanatory. Obviously, if you're doing like the actual GRE, you don't want to take this kind of time to do all of this. Just, do it. And not everything laid out like this necessarily, right? You're not being graded on your work, probably. So you want to just make sure that you run through this and be like, okay, look, I can take 2 and try to plug it into the function up top, because if this is a continuous function, the top and the bottom sections, right, the one that says this complicated function if it's not 2, and k if it is 2, need to be the same value as x approaches 2. And if we just plug in 2 to the top thing, oh no, it's an indeterminate form. Whatever shall we do? Use L'Hopital's rule. Plug 2 into the derivative of the top divided by the derivative of the bottom. The ratio of the fractional portions derivatives. And if you don't know why L'Hopital's rule works, definitely just go over that again. As I've got a series of slides somewhere that has like the full proof of the reasoning in like, in the case where they equal 0, I think. The limits are... that's not quite it. It's like some portion of the top and some portion of the bottom. Oh, the function values are going to be 0 each. So therefore it creates an indeterminate form. Or maybe it's the zeros of the function. There is one at 0. I can't remember exactly what it is. Either way, there's an interesting proof. It breaks it up into like multiple different stages. One of them is like the top and the bottom individually are 0. And then there's another one that it's like dealing with all the infinities and other possibilities. But honestly, if it's not the indeterminate form of 0 divided by 0, you can actually manipulate the functions to turn them into something that equals 0 divided by something that equals 0, and then deal with the original proof based on those instead. It might just be a compound fraction or some weird other thing. It's fine. Okay, k equals negative 1/3 is option D. Cool. In case anybody doesn't know, we're working out of Cracking the GRE Math Subject Test. This is from Princeton Review, 2nd edition, 2002, which again doesn't really change much, but you know, they do occasionally come out with new versions of it with maybe better examples or stuff like that. But overall, the content of each of the individual classes has not changed, essentially. So we tend to just hand wave it and be like, nah, it's the same test. I really should go back and just I don't want to take it again, but maybe grab one of the new prep books and see how much it has not changed. Somebody's got to have a 2020 version, right? Evaluate. Take the limit as x goes to 0 of 1 over x squared times the integral from 0 to x of t plus t squared over 1 plus sine of t dt. All right, this right here is a big feint. It is trying to get you to freak out about it and be like, oh goodness, this is awful. I don't want to have to do this, and just walk away from it. But realistically, what we have here is the limit as x goes to 0 of the integral from 0 to x of t plus t squared over 1 plus sine of t times dt all over x squared. And what do you want to bet? That the top part is going to equal 0 when you get that limit, when you plug in that limit. Well, okay. Yes, it will, because if we put 0 there, then it's an integral from 0 to 0, which is going to end up getting us 0. Right? So we don't. Oh no. I'm off the edge. What? There we go. I think I was aligning it earlier with the URL. Yeah, whatever. Anyway, so yeah, integral from 0 to 0 of anything is going to be 0, so don't have to worry about that. And then x squared at the denominator is going to be 0. So yeah, it's indeterminate, which means we can then take the limit as x goes to 0 still of ddx of the integral from 0 to x of t plus t squared all over 1 plus sine of t dt all over d dx of x squared. That's the limit as x goes to 0 of the denominator is going to be super easy. It's 2x. That's it. The numerator is similarly fairly easy. This is going to end up being a response. Our response to this can be, hey, why don't you look up the fundamental theorem of calculus, part 2 probably, which says, no, it's the first one, which says that the derivative and the integral are inverse operations of each other. So yeah, makes it pretty nice. So what we end up getting with this is that if we think about it, right, this is going to end up getting us d dx of capital F of x because the integral of our function right is going to be capital F of t plus c. And then when we bring limits of integration to it, our t is going to go from 0 to x, which means that we're going to get an capital F of x minus capital F of 0, but then we're taking its derivative, and when we do that, we end up with little f of x minus 0. So the fundamental theorem of calculus is showing us that, okay, well, basically we're just using a dummy variable t to represent what's happening with our little function f of x. And we're taking the integral with the dummy variable t, and then using the limits from 0 to x, and then we're going to take the derivative of it to effectively undo the integration that we did. So it transfers our variable from t to x. So then here, this gives us x plus x squared, all over 1 plus sine of x. Okay, and then we can kind of play around with what we got. So limit x goes to 0 of, here up top we have an x, and this leaves us with a 1 plus x. And then at the bottom we have a 2x times, multiply both top and bottom by 1 plus sine of x. So we have a 1 plus sine of x at the bottom. Then our x's here and here are going to divide out, and we're just left with those bits. Which means we now have a 1 plus 0 divided by a 2 times 1 plus 0, which is a 1/2. And what it's in my hand, see. It is, in fact, option C, 1/2. Other distractors for this one were 1 over 2 pi, 1 over pi, 1, or pi over 2. I imagine pi over 2 would be for people who want to eliminate sine over t immediately or something. Uh-oh. Which part, Zach? Sine of pi is equal to 0? Yep. Yeah. And pi over 2, sine of pi over 2 is going to be 1, so that might tempt some people into keeping that around. I do find it fascinating that 3 of the answers had pi in it. And like there was no talk of pi anywhere in here. And yes, right, of course, you know, sine could have a pi or something plugged into it, and then that would make all the pi's show up where all the x's are. But yeah, still. Yeah, I'm still gonna maybe argue that I don't like that one, but boop. All right. 8. Random logic 0101. Maybe off topic. Trying to teach impulses and momentum to mechanics students. I've been having trouble to get them to grasp Dirac delta. I do not have any experience with the Dirac delta. However, I would recommend if you go check out Dr. Gold at Actual Education. Yeah, you follow. Great. He has a doctorate in physics, so definitely helps. But impulses and momentum. Unit impulse. Okay. The fact that there is a 1 over 2 pi in it makes me think that a good explanation of it is going to involve complex analysis. Or because there is a delta times x minus alpha times f of alpha d alpha, that tells me that in theory you could also use Laplace transforms. Now it may be that it doesn't actually work with Laplace because it's an instantaneous transfer, whereas in Laplace transforms usually you get like over a specific time, but yeah. And that's a joke, random logic, because Zach was just doing Laplace transforms this evening. So also, you could go follow e to the 2 iPi's channel there, and yeah, watch the VOD from tonight. Although to be fair, right, I'm not sure that Zach did this example. Right, so this is the one that involves this one. Signals and systems. Nice. Yeah, and especially as you could have an impulsive signal coming from, like, a radio antenna or something like that, where technically it's just an instantaneous on-off. Technically, it's not instantaneous. It's going to still have a finite duration that is non-zero or non-point, but you know. It could be approximated. Yeah, so I only actually ever went up to Physics 1 and 2. I was originally majoring in physics with the intent on going into astro, which would have been really good because I would have graduated in '05 and we would have been going at either black hole physics, which was like my interest, or exoplanet research, which has become incredibly, an incredibly lucrative field of research in terms of the amount of research. And I know you know this, but anybody else who's watching, have a good night, Zach. We'll see you later. Anyway. But yeah, I would have probably been in black hole research, and like that picture of the black hole being seen from space telescopes, like that probably would have. I wouldn't say that I'd be on that team, but like, I would have felt like I contributed or something. I don't know. It's my field, but as it is, I'm just staring at it in awe from way back over here as a math teacher. It's fine. All right, find the domain. Yep. F of x is equal to, we have the arc sine. But that being said, I have come up with a few interesting little tidbits on my own, and I share them on the channel whenever I can. But in terms of mathematics, so math teaching, I can't say I've like revolutionized anything, but just having a different perspective, always good for students to see an extra perspective that might be slightly different than they've seen before. Arc sine of the natural log of the square root of x. Okay. So what they want us to do first, I am positive, is take this arc sine, take the natural log, convert the square root into an exponent so that we can take that down front, make it the natural log of x. So, this right here, natural log of x, the x must be from 0, non-inclusive, to infinity. Having a 1/2 in front is not going to change from the perspective of the natural log, having a 1/2 in front is not going to change the domain at all, right? That is still going to be from 0 to infinity. However, because this is now within an arc sine, right, we have to consider that the 1/2 is doing something and then figure out what it's doing. So the arc sine right, the arc sine of x has x only between bracket -1 and 1 bracket. And then the transformation of having the 1/2 on the inside is going to force that to expand outward. So and this is one of the things that I have been harping on about with my students, or at my students, I suppose, is that what we've got in many cases is y equals a times f of b times the quantity x minus c plus d as function transformations. And if we use this function transformation stuff, we can then assign, or we can describe any of the behaviors of any particular function based on the values of a, b, c, and d. And they are identical in every possible f. It's just that the particulars of that particular function are going to be slightly different. Right? We take the parent function, and a is going to be a vertical stretch. B is going to be a horizontal compression. C is going to be a horizontal shift. And D is going to be a vertical shift. And every single time that is identical. Every single time. So here with a 1/2 on the inside as a multiplier to the variable term, the variable term being natural log of x. Then what we're going to have is that compared to the original function, the arcsine of x. It's a little bit different, but we'll worry about that in a minute. Right? The arcsine of 1/2 x is going to have x values which go from -2 to 2. Because here what we're effectively doing is multiplying whatever x value we started with by 1/2, then plugging it into the arcsine function. So what's going to get us a value being plugged in of 1? Well, it's going to be an x value in this one of 2, right? 2 times 1/2 gets you 1, and that's a valid number to have for our transformed arcsine. Then we have to say, oh, but, hang on. This is not just the arcsine of 1/2 x, this is the arcsine of 1/2 times the natural log of x, which messes with it even more. So here, normally, right, we're going to have x values that go from 0 to infinity, but it's hemmed in by the arcsine nature of this thing. So we must have x values which go from -1 to 1, or now, with the 2 here, -2 to 2, but we now need to make it the intersection of these things. So now we need the intersection between -2 to 2 and 0 to infinity, which is going to get us x must be from 0 not included to 2 included. What if f is vector valued for this one? This is okay. Calc 2 in my system. Calc 2 is integral. What is it? Integral and numerical methods, and then this also includes here doing like complex domains. This was mostly, I think, in response to up above, we were trying to find the values of continuity. So where, for example, would this function be continuous? All right, we're going to have a continuous function also from 0 to 2, not inclusive. Does Calc 2 change much? I don't actually know. So the individual numbering can even change from school to school, but um, generally speaking, right, in the American system, we have calculus A, B, and C. A is like your basic integrals, derivatives, all that good stuff. B tends to be the integration and some of the basic numerical methods, which I did in my high school course as like, do solids of revolution and stuff like that. I don't know. We might have done Newton's method, but that's derivatives. But I don't think we did actual, like, no, we definitely did not do Taylor series. That was all in technically C, I guess, which I would call Calc 2. So that's like C should be the numerical methods class. Yeah, so for us in the States, typically Calc 3 is multivar. And then, Calculus 4 ends up being real analysis. So it's like, at that point, just stop using numbers. And again, right, if you're starting to run into, oh, but my Calc 2 or my Calc 3 was this, then it's ceased to become helpful. We really should abandon the numbering of the system unless it's just Calculus 1, right? Calculus 1 is the easy stuff right at the beginning, derivatives, integrals, figure out all the Newtonian things. Cool. Yeah. Yeah, I was actually part of a Gates grant which was trying to find a way to standardize all pre-calculus courses across the board. And we got about 5 meetings in and said, we need to standardize calculus in the first place. And this was like a meeting between all of the community colleges in Maryland and University of Maryland, Baltimore College, or Baltimore County. So UMBC. UMCP, College Park, was not interested. They were just like, everybody needs to align to us anyway. And we're like, yeah, no, we're making a coalition. It was kind of fun. We had some really awesome people on that group, too. We actually had a guy who was on UMBC faculty who, I mean, he'd been there forever, right? But at the time of publication, we were like, okay, so we're writing a real, actual like paper for this, right? And then we all kind of look around the room and go, who's got an Erdish number? And a couple of people raised their hand, and they were like, like 4, 6, something like that. And this guy raised his hand and goes, 2. Everybody's like, ooh. I would like to be a 3. Yep. That's a problem. I did not do this correctly. Or at least we did not consider something. Yes. Okay. The problem here is that we're taking a natural log. So, when do we get a 2? Hey, Raven. How's it going? Okay, so this is not the final step, actually. Oops. I lied. So the 2 needs to come out of the natural log. So what is the exponent on a power of e that is going to get us a 2 back? Right, so natural log of x is equal to 2, which means no, okay, I went backwards. Of course I went backwards. I teach pre-calc. Right. Natural log means what is the power, which on the other side tells us. The power is 2 on a base of e, and it'll get us x. Right, so here, you can't see that. This is going to end up with e to the natural log is just going to drop whatever it was holding, is going to be e squared. Okay, so that's where it starts. And when do we get a 0? Because that is not going to be, right? This is not, in fact, x. It's the natural log of x needs to go from 0 to 2. No. No. Natural log can go all the way back. The value of the natural log can be -2. So natural log of x, no it can't. Yes it can. Jeez, man, come on. Alright, natural log of x is -2, so the exponent on a power of e is -2, which gets us x. So x is going to be equal to e to the -2. Okay, that looks better. Jeez. So x is going to be equal to, this is e to the -2 to e to the 2nd, and it is possible to be both of those values. Now we should be good. So 1 over e squared to e squared bracketed. Yes. Okay. Oops. So Raven, that's exactly what I did in my head. It's the x which can be 1 to get us 0 back, but that's not what the question was asking, and I skipped over some of that in my head. So, thanks everybody for coming. I will be back in 3 minutes. We got our first ad break coming up, and I'm gonna probably get some more water, I suppose. And turn off the shared processing thing that's been eating up my processing power for the last hour. Yay. Alright, see you in 3 minutes. Thank you so much for coming. Be right back. All right, so probably a stupid idea because I already warmed up earlier. I'm not gonna do a warm up. Lol. I have been basically attacking the air all night and just like playing around with all sorts of karate and Tai Chi mix, and so I think I'm more or less warmed up anyway. So, we're going to do the Tai Chi form. I'm actually going to start, I think, facing this way because I need the extra room on this side. So, start in bear formation, more or less. Feet in a V, and we tuck into the right hand side, inguinal crease. It's that space between your quads and your abdomen. There's that nice little crease in here where a lot of people think the chi comes from. However, it is entirely non-mystical and biomechanical. Sorry to disappoint. Tuck into the right hand side, step and straighten out. Standing about, shoulder width apart, even with each other. Cool. We breathe in as we bring our hands up. And then out as we bring them down. From here, I'm going to tuck into the right hand side. That's the left. Tuck into the left hand side. Sink down on this side. Turn and grab the energy ball. Turn 90 degrees with the right foot. And then we lean forward. I feel like I'm really off balance here because I'm not used to it facing this direction. It's crazy. All right, we step left and then come the other way with a ward off left, right hand drops, and then right foot twists. Once we get to about here, we're going to tuck ever so slightly into the left side, but the main point is to turn on the ball of the right foot and then step out again. And as the weight shifts, do a ward off right. Looks like that. And then we bring all of this down into a ward off. So as somebody attacks, basically we're standing like this, leaning forward, and then as someone attacks, or if they try to put forearm to forearm and start pressing in to into your center, then what you do is you do a roll back where we bring the left arm, which is here for our structure, collapse it in a little bit, point more or less toward the forearm or elbow on the right hand side, and turn while shifting the weight back. This allows somebody to essentially just fall right through your guard, and they'll typically go that away. If they're committed to the movement. If they haven't, then you might be able to catch them off guard anyway. So, do a rollback, put our hands together and do a press, which reinforces our guard and then can also knock them slightly off balance. Separate the hands, lean back, and then push. And that push allows us to push the person back away from us. Okay, and then from here, we lean back, twist the right hand side this way. Now we're in this kind of like awkward pigeon toed sort of thing. So what we do is we come back around this way, tuck into the left inguinal crease, and we have our hand down like this. And as we shift weight back, we also pick up the front heel, go onto the toe, and it allows everything to kind of uncoil. We're going to bring out the left hand, left foot, and then as we shift weight back to the front, we're going to twist the hand, move the foot up, and shift the weight to the front side. Then bring everything down, lift hands. We're on the heel of the right foot, basically no weight on it at all, just to hold it in place. And then we bring everything back in and do a shoulder drop. So this is going to impact against the person, possibly with the elbow, possibly with the shoulder. You just do it anywhere in there. And then we do white crane. This is actually going to be more that way. Cool. So we're up on toes on this side. And then from here, we want the hips to be square to the front. We're still at like 90 degrees. This is very taxing on the right quad. And we bring this down as a right kind of like sweep block. So it's going to come out and sweep. Left's going to come in as well. And then when the right hand comes back up around our head, we move forward, both sweeping this out and using this to slap or knock or do whatever move we're going to do. But for the form, right, this is essentially a tiger strike here to the face. All right, and this is also blocking anything that's going for the knee. It's called brush knee. Then we step forward 90 degrees and strum the lute, which is a lot like lift hands, but on the left-hand side and slightly different. I'm not entirely sure what the difference is. It's fine. From here, I need to move back. So we're gonna again, almost no weight on the left-hand side. We're going to do another. Again, make sure that the hips are more or less aligned with the front. And here we do another brush knee. So this is going to, again, go like this. Then what we do is we lean back, tilt the forward foot 45 degrees, and as we start moving forward, the right hand comes down into a fist. Then we're going to come through, step 90 degrees with the right foot. This is essentially going to be aiming for the other person's ankle to try and break, or you hit their leg and put all of your force into it. Could break the leg anywhere along the lower part, but mostly it's going to go for the ankle. So we are here, come through 90 degrees and twist. Oh, that was a terrible one. Hang on. We're still 90. Okay. So we come this way. This came down. All right, this is going to be more at the hip. This is coming across as a parry, and we're potentially going to block anything that's up here. This needs to be 90 degrees. And then we're going to step through and punch. And here, this is going to be here either to lift up the person's arm here so that you offer a much larger target. Go for some floating ribs, especially. All right, from here, what we do is we're going to tuck into the left inguinal crease. We're going to do a rollback with all of our weight kind of leaning forward. This hand is going to circle around to under the elbow. It's going to take the weight of the other person's guard or whatever else is against our right hand. So basically you just transfer the weight of whatever's here onto the other hand, loosen up the right hand and let it just kind of fall out, but you don't want to like literally flop. So by offering no resistance on the right hand, we're able to just slide out, transfer, and push. Then from here, we're going to do the exact same thing that we did earlier. We're going to lean back, and then this is going to twist left into this weird pigeon-toed stance thing. But instead of doing any of that other stuff, what we do is we just come out with our hands, retreat back to shoulder width, feet aligned with each other and all that good stuff. And then these hands come up. Right hand is going to be behind the left hand, and then we're going to hang the left hand sort of on it and lean a little bit to the left. After that, that is the complete like first third of the form. There's some other stuff here that goes into cool, like using all four of our moves. The ward off, rollback, press, and push, and alters how exactly you see them. So I'm going to learn some of that stuff Saturday, next few weeks, whatever. We'll see how that goes. I mean, it's going to be awesome, but nonetheless. Okay. So hi, welcome to Tai Chi. All right. Right. That is going to be our solution for number 8. Number 9. Evaluate the derivative of f of x is equal to the arc sine of the natural log of the square root of x at x equals e. This is what tipped me off to say we did the above wrong, because we got a interval that was from 0 to 2, and quite clearly 0 to 2 does not contain e. So yeah, knew I did something wrong. So we got it. Now, we did say that the other way to do this is we could say this is f of x is equal to arc. Oh, there you go. Arc sine of 1/2 times natural log of x. So f prime of x is going to be equal to the derivative of the arc sine. Oops. Is going to be 1 over the square root of 1 minus x squared, I believe. What do we got? Do we have calculus? Areas between curves. Sounds good. Nah, it's going to be Calc Volume 1. Oh well. Oh, yeah. Change the number. Calculus Volume 1. Table of contents. Derivatives of inverse functions. Oh, no. That's not, no. That is not what I wanted, actually, but it's fine. It should be in the implicit differentiation chapter. It would have been faster just to do this myself, honestly. Trigonometric functions. No. That's interesting. No, that's not what I want. Hang on. Right, because that's not... This is in Chapter 1. That's before we actually do any of the other stuff. Right. Oh, come on now. Collapse Chapters 1 and 2. Differentiation rules. There we go. Arctic flounder? No. I typed arc sine. You cannot possibly tell me that Arctic is what I wanted. But hey, maybe I just don't know what I want. Really? Alright, whatever. It's not Chapter 1. Pretty sure it's Chapter 3. Derivatives of trigonometric functions we already looked in. No. I mean, right, the free exercise bits are easy enough to find here. No, I'm looking for the derivatives of the inverse trigonometric functions. So right, this. Right, because we're taking the derivative of the sine of y in order to get the other trigonometric. Seriously, this is going to be just faster for me to derive them. So sad. Right? So this is sine of y is equal to x. And yes, I could look them up faster, but you know what? It's fine. Here, this is going to be 1 is equal to the cosine of y times y prime. So then, cosine of y, we know that the sine of y is equal to x over 1. Nope, over 1. So that means that this one is going to be 1 minus x squared. Cool. Yes. Which means that the cosine is going to be equal to the square root divided by 1. Okay. So this is the square root 1 minus x squared times y prime is equal to 1. So y prime is equal to, and that's where we get that. It's also good exercise to remember what all of this stuff is. So that I don't just like come up with an answer and be like, yeah, it's this, and everybody's like, I don't get it. Right? It's going to be important eventually to remind ourselves what, or like, how do you get the answer? How do you actually derive the answer? So yeah, implicit differentiation, because it's arcsine, you can flip around variables on that, and now you're trying to find the sine of y being equal to x. And drawing these pictures, the diagrams with all of the sides being listed as the sides that are here, is also a really good reminder, right? It's x, so of course it's x over 1. Sine is a ratio. All that stuff. Anyway, with f prime, we have the derivative of arcsine is 1 over the square root of 1 minus parentheses, all of the stuff on the inside, 1/2 natural log of x squared, times the derivative of the inside is going to be 1/2 times the derivative of natural log of x is 1 over x. Good. So this is 1 over 2x times the square root of 1 minus parentheses 1/2 natural log x squared. Okay, this is f prime at x. We wanted, when x is equal to e, so f prime of e is going to be equal to 1 over 2e square root 1 minus parentheses 1/2 natural log of e, which is 1, times 1/2 squared. So that's going to be 1/4. So 1 over 2e times the square root of 1 minus 1/4. It's going to be 3/4. 2e square root 3/4, which is going to then be 1 over 2e times root 3 times 1/2. So square root of 1/4 gets us 1/2. That's going to knock out the 2 from the front. So f prime at e should be 1 over e root 3. Is that an option? Yes. 1 over e root 3. Other options were e over root 2, I guess, pi e over 2, because the arcsine would be 0. I guess if you messed up and said arc cosine, that could be pi over, sorry. Could be if we had a value of -1, but like there's no -1 there. Apparently it's said often enough, some students might actually get it. Root 2e. So at some point my spouse did have 2 root x, which could be then 2 root e rather than the square root of 2e. So in theory, right, it could theoretically have come up with something similar to that, where a student might be like, oh yeah, sure. Or 3e over root 2, which is pretty much the opposite of what we ended up, not exactly opposite, but if you switch the 3 and the 2 in terms of what's inside and what's outside, I could maybe see how somebody did that. Anyway. Okay. Number 10. Okay, for what values of m and b will the following function have a derivative for all values of x. Okay, so this is very distinctly, importantly different than the other one we did back here, where it was just asking what value of k, a single number, is going to make this function continuous for all x. We were, first of all, just filling in one single point. Right? This was a removable discontinuity. That's all we needed to do was just put it in the point itself. However, this one is not just asking, right, just will it be continuous? So first of all, in order to have a derivative, there are two major conditions. One is that all, we're running actual music? Yes, okay, good. I know we're getting up toward the end of my playlist, I think, but one, it needs to be continuous on the same. So here we're saying for all values of x, therefore it must be continuous everywhere. So we need our, first function let's say it looks like this. Right, we need the first function to be continuous. So this clearly is not going to work because we need this to fill in the blank here. But then also, condition 2 the limits of the derivatives must be identical. So in this particular case, it is no longer sufficient to just say, do that, right? Fill in the dot. It doesn't work anymore. What we have to do is say, okay, we're going to take this and we're going to make it so that it does, in fact, have the exact same slope as the thing on the other side. Because if it doesn't, then we fail the second condition. We're not going to be able to have identical limits of the derivatives of both sides. Okay, so the function itself, f of x is equal to, we've got the system x squared minus x minus 3, no, plus x squared plus x minus 3, if x is less than or equal to 1. And mx plus b if x is greater than 1. Okay, so condition 1. We know that the function values need to be the same, so the limits of the original function from either side need to be the same. So we have the limit as x approaches 1 from the negative side of f of x must be equal to the limit as x approaches 1 from the right-hand side of f of x. Okay, this is going to have two unknowns, so it doesn't really help. We're going to go here. This is going to be the limit as x approaches 1 from the negative side of x squared plus x minus 3 must be equal to the limit as x approaches 1 from the right-hand side of mx plus b. Right, so as it's approaching 1, we just get 1 in for x. So here we have 1 plus 1 is 2. Minus 3 is going to be negative 1 is equal to 1 in for x is going to make m plus b. That's it. Okay, so can't finish it, but we'll come back. Step 2. And we should again change color. The derivatives must be identical. So the derivatives, the limits of the derivatives, the limit as x approaches negative 1, no. X approaches 1 from the negative side, very different than approaches negative 1, of x squared plus x minus 3, parentheses, derivative. dx must be equal to the limit as x approaches 1 from the right-hand side of the derivative of mx plus b. So here we have the limit as x approaches 1 from the left of 2x plus 1 must be equal to the limit as x approaches 1 from the right-hand side of mx plus b. We take the derivative, we're left with just m. That's it, right? Just the slope. So our slope must be the same as, plug in 1 for x here. This is going to be 2 plus 1, which is 3, equals, on the right-hand side, there is no x anymore, so it's just m. Right, so m is 3. Then we back substitute, say m, if m is 3, then we get 3 plus b is going to be equal to negative 1. So subtract 3 from both sides, we get negative 4 is equal to b. So y equals 3x minus 4. Right, that is going to be the equation of the line, which allows for us to have a derivative at every single point. And if you want to show it off, right, then you go with x squared plus x minus 3 when x is less than or equal to 1. Make that nice and big so everybody can see it. And then here, this is where we do 3x minus 4. and make it so that x must be greater than 1. All right, so 1, -1 is going to be the point where these two things appear to be, even though you can't evaluate it on the blue side. Again, we could find the limit, plug in 1, or sorry, -1. Plug in -1, we end up with, wow, no, the x value is 1, so plug in 1. And for the blue one, we do get 3 minus 4, so that's -1. Cool. And then again, we can prove that, yeah, the slopes are the same by taking the derivatives of both and making sure that their values both come out to 3. We know the line, that's easy. And then we just take the derivative of the parabola, get 2x plus 1. At 1, 2x is 2, plus 1 is 3. We're good. Right. That is the first 2 pages of the review questions done. Let's see. Ugh. We have a few more. Right, there are 50 questions in this thing. Hopefully next time we'll do a few more, just to try and catch up. I'm getting a bit tired, so I should have started earlier. But I still have to do my trivia anyway, so. Alright. We'll try and figure out somebody to go visit for the night. Hope everybody is having a good time. We have a YouTube page for anybody who does not know. In fact, we have 2. One for our gaming content at Obi-Wan Pez, and one for our math content, as you see before you, at nsimplex pachinko 6542. If you just search for nsimplex pachinko, you'll find it. It's there. And I do tend to upload those on a, 2 weekly basis. I finally sit down and actually do it. So we'll see how that goes. If you would like to follow any of our other awesome math streamers, we have this list right here. Still not complete. Damn. Academy of Useless Ideas. That's Slim. Dr. Gold at Actual Education. Don Factorial. E.N. Stuckey. Zach from E to the 2i Pi, Merriweather Remark, Penn Center, Phobos Dream, Physics and Depression, and the Tutor Wizard. Oh, and Talos Teaches. We also have Math Pond, who is Matt. And Matt likes ducks, so if you like ducks, it's a good place to go. We also have our study buddies who typically do some mathematical content, but it can be whatever they're learning this week. So if you like learning about new stuff, you can go check out Rendeo, Math Spellbook, FizzBuzz, Suna Owl, or Walking Stick Library. And there are many other people who are out there who are really awesome. We often go see Mahoodles, Astro Canuck, often, right? I mean, how often is often? Paleontologizing, who is Dr. Danny Anduza, who is a paleontologist. When they're on at the same time, Rock It Sage, who is a geologist, Science Streams, who are ant biologists. I forget exactly which subfield, but anyway. And Volcano Doc, who is a volcanologist. So let's go figure out who is on tonight. We also have, just real quick, a friend of Science Streams um, named Irish John Games just released a game on Steam in the early access greenlit project area called Rise of Piracy, and we played that yesterday. So anyone who's willing to give it a grape shot, we'll see you all on Rise of Piracy. Uh, it may or may not have multiplayer. I don't think it currently has multiplayer stuff, but it might eventually. It's just really cool because like he worked really hard on this. He's been doing stream sessions for like 5 years, and he finally has released it. It is out. It is quite good. I like it. It's fun. And I was telling everybody earlier over at Zach's that I created a character that was like full on mercantile and like is peaceful, definitely will defend themselves, but like is growing a fleet just by like buying and selling stuff and doing missions around. So we're doing okay. I'm also going to eventually create a pirate character who is just all in your face, going to destroy every ship possible. So we'll see how that goes. I think at some point we're going to also do like a privateer, basically, who's going to just cause conflict and strife and get some sort of diplomacy going to like destroy everything that's basically get a zero reputation with everybody. But it's probably a terrible idea, but I like it, so probably eventually going to do that too. I doubt we're going to do all of those on stream. Right, we have Winning Sequence, who is doing Pie Plays Pokemon Sapphire. They have, for the last 4 years plus some, just let the numbers of pi determine what the next action is going to be. Yep. We have Rhaekodactylus, who is currently doing modern tech misinformation research. Maybe where we're going. We like Rhaeko. He's fun. Crit Bard is a friend of ours who does currently doing Legend of Zelda Twilight Princess. Casey Snow Art is on doing a Fire Horse illustration. Nice. Paleontologizing T-Rex ran like a bird. Alvarez Soar Evolution Shakeup. Nice. And a four-eyed vertebrate ancestor. Interesting. Alright, that's who we got tonight. So let's head over to Reiko's channel. And we'll see you all a bit later. On Friday, I should be doing Against the Storm. It is possible that we could decide to do some Rise of Piracy as well, just because, it's that week. I'll probably be throwing out another character somewhere and doing some more Rise of Piracy and or trying to remind myself how to do diplomacy and land attacks and stuff like that. So I will see you all later. My name's Obi-Wan Pez. This is N Simplex Pachinko. Have a good night.